Assigning oxidation numbers. So first we're going to review on how to assign charges on elements. So the problem says to write the ions within each one of the following compounds. I'll show you how to do this with the first one, and then I'd like you to try the other ones on your own. So for this first one, we have calcium carbonate. So for calcium carbonate, we have Ca, and calcium has a 2+ charge, and carbonate is a polyatomic ion, 2 minus. Calcium is 2+ because it's in group 2A on the periodic table, and carbonate is at polyatomic ion, which the charge is listed in the table of polyatomic ions. So that's what you would have for your answer. You should pause the video, go through the rest of these, and try to come up with the charges on each one of these. Okay, so hopefully you had an opportunity to do this. You are going to flip up charges, or you can get the charges from the periodic table. So potassium has a +1 charge, and chloride has a -1 charge. When we have something like this, we have to figure out what form of iron this is. Is it iron 2, iron 3? So when we flip up the charges, this becomes Fe plus and SO4 minus. However, SO4 actually is supposed to be 2 minus. So we have to multiply that by 2. So that means we're also going to have to multiply iron by 2 to get to the true charge of iron. So the true charge of iron then would be Fe2+ and sulfate SO4 2 minus. Magnesium chloride, we can flip up the charges or get these off the periodic table. Mg has a 2+. Cl minus. We can flip up the charges here. Zn gets 2+. PO4 is 3 minus. And ammonium nitrate, NH4+, NO3 minus. So now that we've reviewed charges, we're going to talk about oxidation numbers and oxidation reduction reactions. So redox reactions are taking place all the time in the body. Anytime your cells produce oxygen, there are harmful substances, anytime your cells use oxygen to produce energy, there are harmful substances that are produced as a byproduct. So we have antioxidants in our body to try to neutralize those free oxygen radicals. Oxygen can cause a lot of issues when it's combined in certain ways. So we have to neutralize the toxic effects of oxygen, and that can slow aging and slow cellular death. Oxidation is also something that happens to metals when metals rust. So they're exposed to oxygen, oxide compounds are formed, and that becomes a chemical reaction on the surface of the metal. So how do we prevent all this? Well, we have to know a little bit about keeping track of oxidation numbers and assigning oxidation numbers to different components within compounds. Oxidation numbers are not the same thing as the charge. So although it's important to be able to determine the charge of ions within molecules, that's not what we're doing with oxidation numbers. The charge of the ion does not change no matter what it is in a compound with, but the oxidation number might change depending on what it is in a compound with. Oxidation numbers are not always the charge of the ion. So the oxidation number or oxidation state is an integer that's assigned to each element in a particle that allows us to keep track of electrons associated with each atom. An oxidation number of 0 means the atom has the same number of electrons assigned to it as there are in the free neutral atom. So elements are given 0. A positive oxidation number means the atom has fewer electrons assigned to it than the neutral atom. A negative oxidation number means that the atom has more electrons assigned to it than the neutral atom. Electrons have a negative charge. So if you have a negative oxidation number, you have more negative charges. If you have a positive oxidation number, you have less negative charges. Rules for assigning oxidation numbers. So these rules are spelt out in the chemistry aid sheet. So you should review all of the details that are listed there, but this is just a short summary. So an uncharged element is 0. Monoatomic ions, so if you just have like Na plus or Cl minus, those are given the charge of the ion. Combined fluorine is always -1. Combined oxygen is -2, but it's -1 in peroxide compounds. And covalently bonded hydrogen is +1 with no exceptions. There is a link to a video that goes through how to assign oxidation numbers, and it goes through a couple different examples and different perspectives of oxidation numbers. So I strongly recommend that you watch that video, but I'm going to go through how to use the oxidation rules to assign oxidation numbers. The first rule is you always want to start with the most electronegative compound. So there is a table of electronegativity on the same page that you'll find the oxidation numbers on. So between fluorine and oxygen, you can see that fluorine comes first. So we are going to assign fluorine an oxidation number first. So according to the rules that are listed here, it says that group 7A bound elements, so fluorine, chlorine, bromine, iodine, antimony, we have oxidation number is usually -1 unless it's bound to an element that is more electronegative, but it also says that fluorine is always -1 because fluorine is the most electronegative compound. So right away we can give fluorine an oxidation number of -1. Now the oxidation number on this whole compound has to add to 0. So we have one oxygen, and I'm going to put oxygen as X, plus we have 2 fluorines, and fluorine we determined to be -1, and we're going to add that to 0. The reason why the whole compound is 0 is because there's no charge on this compound. If it did have a charge, we would set it to the charge on that compound. So we have X -2 equals 0. So X has to equal +2. So the oxidation number on oxygen is +2. Going to the next example, we are going to assign the more electronegative element first, which happens to be oxygen. Oxygen is going to be assigned according to the rules here. Oxygen, the oxidation number is usually -2 unless it's bound to fluorine or it's bound to another oxygen like in peroxide. If either of these apply, you must calculate oxygen. Well, neither one of those apply, so we're going to assign -2 to oxygen. Now the sum of this whole thing has to equal to 0, so we have 2 fluorines, which I'm going to just put as X, plus we have 3 oxygen, and oxygen was already determined to be -2, and we're going to set that equal to 0. So 2x minus 6 equals 0. 2x equals 6, divided by 2 divided by 2. X is equal to 3. So the oxidation number on iron is plus 3. When assigning oxidation numbers, we always want to put plus or minus. So it's either a positive oxidation number, it's a minus oxidation number, or it's 0. 0 obviously doesn't need the plus or minus. So now we have carbon and hydrogen. So we're going to assign +1 to hydrogen because the rule says the oxidation number is +1 when bonded to nonmetals. So hydrogen is going to be assigned +1. Let me clean this up a little bit. There we go. So hydrogen is going to be +1. And the whole compound has to equal to 0. So we have 1 carbon, and I'm going to put an X for carbon, plus we have 4 hydrogen, and hydrogen was already determined to be +1, and we set that equal to 0. So we have X plus 4 equals 0. So X has to equal -4. Now we have this big guy. So first we're going to assign the most electronegative. So we're going to give this one an oxidation number of -2. Because according to the rules, it's -2 unless it's bound to fluorine or another oxygen like in peroxide, which it's not. So now that we have -2, we can start looking at the other ones here. Group 1A is given an oxidation number of +1, and hydrogen is usually +1 unless it's bonded to metals. So it's +1 when bonded to nonmetals. Because this is what we're looking at here, the sodium is not directly bonded to the hydrogen. The hydrogen is directly bonded to the CO3, the carbonate group. So this actually is given a +1. So now we have 1 sodium plus 1 hydrogen plus 1 carbon plus 3 oxygen, which oxygen has already been determined to be -2, equals 0. So we have 2 plus X minus 6 equals 0. We combine the 2 with the -6, we get X minus 4 equals 0. So when we move the 4 to the other side, we get X equals +4. So carbon is assigned the oxidation number of +4. Okay, so go ahead and pause the video and fill this in with the oxidation rules. Okay, neutral elements are always 0. In a compound, group 1 metals are typically +1. Group 2 metals are typically +2. Hydrogen is usually +1. Oxygen is usually -2. Group 7A usually -1. Fluorine is always -1. And the sum of all the oxidation numbers is equal to the charge of the compound. So if it's an uncharged compound, it's equal to 0. If it has a charge, it's equal to that charge. Again, you want to start with the most electronegative atom first. So this is our table of electronegativity. You should always reference this when assigning oxidation numbers. So write the oxidation number of each known atom below the atom in the formula. Multiply each oxidation number by the number of atoms of that element in a compound. And then write an expression indicating the sum of all the oxidation numbers in the formula. So oxygen is -2 since it's more electronegative element. So when we're tackling this first one, we give a -2 to oxygen. So then we have 2 of the nitrogen, plus we have 1 oxygen, which is -2, and since the whole thing doesn't have a charge, we're going to set that equal to 0. By the time we're done with the algebra, we can see that N is +1. So the oxidation number on nitrogen in this instance is +1. But what about in this instance? We assign the oxidation number of -2 to oxygen. Now we have 2 nitrogen plus 3 oxygen is equal to 0. When we do the algebra and solve for nitrogen, we see that nitrogen has a +3 oxidation number. And O2, again, we do the algebra and we end with +4 as an oxidation number for nitrogen. So oxidation numbers of elements can change depending on what they are bound to. That's why we have to calculate them. We can't just take the charge from the periodic table, we actually have to calculate it. So the oxidation number of nitrogen in all these different compounds can be different. So the oxidation number of ions. So here we have Cr2O7 2-. Now we have 2 chromium. We know that oxygen is going to be -2 because that's a rule, and we have 7 of those -2 oxygens. We're going to set this equal to the charge because a charge is listed. When we do the math, Cr is +6. Another example here, carbonate. There's 1 carbon. Oxygen we know is -2 because it's a rule. So we have 3 times -2, and we set that equal to the charge, -2. When we do the algebra, we can see that C is +4. HSO4, we have hydrogen, which is +1, oxygen, which is -2, and we have to solve for sulfur. So we have 1 sulfur, which we don't know what it is. We have 1 hydrogen, which is +1. We have 4 oxygen, and each oxygen is -2. And we're going to set it equal to the charge on the compound of -1. When we do the algebra, S is +6. So here is a practice question very similar to what you would see on an exam. What is the oxidation number of manganese in MnO2? Okay, so we're going to assign -2 to oxygen because it's a rule. So we have Mn, and we have 1 of those, plus 2 of the -2's for oxygen, and there's no charge on this, so we're setting it equal to 0. So Mn minus 4 is equal to 0. Mn has to be +4. What is the oxidation number of sulfur in H2SO3? Go ahead and pause and try to solve this one. All right, so again, oxygen is -2. Hydrogen is going to be +1. So we have 2 of those hydrogens plus we have 1 sulfur, and I'm going to put X for sulfur, plus we have 3 of the oxygens, which are set to -2, and we're going to set that equal to the charge on it, which there's no charge. The reason why I use the letter X is because it can't be mistaken for a number. If I put the letter S in here, you may think that's the number 5. If I put O for oxygen in here, you may think that's 0. So just so we can keep it clear, I like to use X, but it's your choice what variable you put in there. So now we have 2 plus, let me clean this up a little bit, 2 plus X minus 6 equals 0. We have X minus 4 equals 0. X is equal to +4. So the oxidation number on sulfur is +4. Oxidation number of carbon in C2O4 2-. Oxygen is given -2, so we have 2 carbons plus we have 4 of our -2 oxygens, and we're going to set it equal to the charge. So now we have 2x minus 8 equals -2. We're going to add 8 to both sides. 2x equals, so +8 plus 8 plus 6 divided by 2 on both sides. X is equal to +3. Okay, so go through this list and determine the oxidation number for each element or compound that's listed here, and then we'll unpause and go through these together. Okay, first one, it's elemental. This is just going to be 0. Second one, also elemental. This is going to be 0. Here we have to determine what the CO, the C, and the O are. O is going to be -2. And now we have a problem, and we haven't encountered this problem before, so we can figure this out though based on the polyatomic ion. There is no rule for cobalt, and there's no rule for carbon. So what do we do in this instance? Well, we can separate out our polyatomic ion to figure out what carbon is. So if we do that, we have CO and CO3. If we separate this out, we can chunk out the CO3, and CO3, if we separate it, has a 2- charge. We know that the carbonate has a 2- charge. So we have to put the appropriate charge on it when we do separate it out here. So now we have -2 for the oxygen, and we don't know what the carbon is, and that's what we're trying to calculate. So we have 1 carbon plus we have 3 of those -2 oxygens, and we set it equal to the charge of the polyatomic ion. So that's X minus 6 equals -2. We're going to add 6 to both sides. So X is equal to +4. So the carbon is +4. Now the other cool thing that we can do here is, in order to calculate the cobalt, we can simply say that since the oxidation of this sums to -2, because that's the charge of the polyatomic ion, and that's one of the rules that's listed on the chemistry aid sheet. The sum of the oxidation numbers in a polyatomic ion is equal to the charge of the ion. So if this side of it is -2 and we eventually want to get to 0, this side of it must be +2. So we can automatically calculate what that would be. So if you don't want to take the shortcut route, we can go back and calculate the whole thing. So if we have 1 cobalt, which we don't know, plus we have 1 carbon, and we determine carbon to be +4, plus we have 3 oxygen, which is determined to be -2, and we set that equal to 0, we end with x plus 4 minus 6 equals 0, x minus 2 equals 0, x is equal to +2. So however you want to think of it, when you identify a polyatomic ion, you can use the charge to your advantage. You need to separate out the polyatomic ion, figure out what the charge of the carbon is first, and then you can go back and do the rest. So these problems you only have to worry about if you do not know if there's no rule for multiple elements within there. So this is probably the most complicated problem you'll encounter. So let's go back to this. I'm going to clean this up, and now we'll go on to the next one. So CSH, H, so we have to find cesium on our CS to determine electronegativity. So go to your table of electronegativity. Hydrogen is definitely higher, and cesium is a metal. So oxidation number is -1 when bonded to only metals. So this is going to be -1, and this is going to be +1. So according to the rules, we found our element of higher electronegativity, and that was hydrogen. Hydrogen's rule says it's -1 when bonded to only metals, so we gave hydrogen -1 and cesium +1. Next one, we have oxygen is going to be -2, and there's a rule for sodium, which is +1. We still want to calculate it just to make sure. So we have 1 oxygen So, sorry, my pen is acting up here. So we have Na2O, and we said oxygen is -2. So we have 2 sodium, which we don't know what sodium is, plus we have 1 oxygen, and oxygen is -2, and we set that equal to 0. So that becomes 2x minus 2 equals 0. 2x equals 2 divided by 2 on both sides. X equals +1. Now if we look at the next one, Na2O2. So because oxygen is bonded to itself, it's technically considered a peroxide compound. And in peroxide compounds, it says that the charge is going to be you have to calculate it. So if it's bound to another oxygen, like in peroxide, you need to calculate it. So we are going to assign +1 to sodium, and then we're going to calculate the oxygen. So for Na2O2, we're going to assign +1 to sodium, and there's 2 sodium, plus there's 2 oxygens, and we're going to set that equal to 0. So now we have 2 plus 2x equals O. So we're going to move this 2 over. 2x equals -2. Divide both sides by 2. X is equal to -1. So the oxidation number on sodium in here is +1 still, but oxygen is -1 in this instance. This next one, we have a polyatomic ion here. So this half of it has to be equal to, and let me get some more space again. I'm going to clear this out. We're going to recognize this and break this in half. This half is going to be equal to the charge on the polyatomic ion. So sulfate has a -2 charge. So if this half is -2, then this half has to be +2. Coincidentally, there's also a rule for calcium. So either way we look at it, calcium's going to be +2. But now we have to figure out what sulfur is. So we're actually going to chunk away the SO4 polyatomic ion and set it equal to its charge. We know that oxygen has a -2 oxidation number. So we have 1 sulfur plus we have 4 oxygen, and the oxygens are -2, and we're going to set that equal to the charge of the polyatomic ion. So we have X -8 equals -2. We're going to add 8 to both sides, and that gives us X equals 6. So sulfur is 6 plus 6, and oxygen is -2. Oxygen here is -2, beryllium is then +2, and that's because they have to sum to 0. And that leads us to our last problem, P2O5. So P2O5 my pen is probably dying. P2O5. Oxygen is going to be -2, and we assign that one first because it has a higher electronegativity. So we're going to do 2 times X for phosphorus plus 5 times the -2 for oxygen equals 0. 2x minus 10 equals 0. We're going to move the 10 over to the other side. 2x equals 10. Divide both sides by 2. X is equal to 5. So oxygen is -2. Phosphorus is +5.